This is the problem that we're going to work through. The function f has a continuous derivative. If f of 1 equals 2, f of 3 equals 6, and the area under f of x between 1 and 3 is 8, what is the area between 1 and 3 of x, f prime of x dx? So what we're going to do is we are going to make a little xy plane, so like this. I'm just going to use base 10 blocks for this. And this is what it will look like. Make that a little straighter. Okay, so this would be our xy plane. Just put that up like that so you can see it. It's not totally straight, but it doesn't really matter. So this is our x and our y. Okay. The area under this curve is between 1 and 3 is 8. So from, it says f of 1 is 2, so we go here. And then f of 3 is 6, so we go 3 over and 6 up. So this is 1 over 2 up. And then I should really say 1 to the right and 2 up. And then this line just connects them. Okay. Now, you wouldn't necessarily know that that's a straight line, but I've done the work and I can tell you that it's a straight line, so I'm going to do a straight line. But to be honest, you would just draw some curve there. You wouldn't really know what it looks like if you're not given what the function is, because we're not told what f of x is here. Okay. But in the end, it's pretty easy to work out. It says that that the area under this curve from 1 to 3 is 8. So what we're looking at is down here and down here. This area in here is 8. Okay? And what we can see here is that there's a little rectangle over here. I think online a lot of people refer to them as boxes, the big box minus the small box, but with Mortensen Math, we use rectangles to facilitate counting, and so it's a large rectangle, subtract a small rectangle, for because this is basically integration by parts, okay? Integration by parts basically is this. It says that you have some starting point A, some ending point B, and it's u dv equals uv on AB minus the integral of AB of v du. Okay, it looks kind of complicated, right? But it's actually not that complicated at all. Basically, this part here is the part that we're going to look at right now, and that is basically a big rectangle subtract a small rectangle, because in this case we are between 1 and 3, and so this would be a 3, that would be a 1, that would be a 3, and that would be a 1. Okay, and this here is just this area here, the 8, right? And so if we take the big rectangle here, which is 3 times 6, that's 18, and we subtract the small rectangle, which is 1 by 2, right, we get 16 subtract 8, and we're actually left with 8, which means that on this side we are left with 8. So this is 8 and that's 8, and you can actually see this because 1, 2, 3, 4, 5, 6, this basically is 7, and that's 8. Well, look up here, 1, 2, 3, 4, 5, 6, 7, 8. Well, 8 and 8 is 16, 17, 18, and 3 times 6 is 18. So you don't really need to have this, you have to understand what the formula is saying, and I guess that's sort of what the point is that this very complicated thing is just really a big rectangle, subtract a small rectangle, and then subtract the area under the curve, which they give you, which is 8. Right, well, the big rectangle here is 18, the small one is 2. right? Well, 18 subtract 2 is 16, subtract 8 is 8, which means over here, this area here has to be 8, and this is this area above the curve here, okay? So let's actually just look at how you would solve this. What we would do is, if we're integrating by parts, is we're looking for this area here, right? So I'll just underline for a minute here. That's what we're looking at here. We would let u equal x, and then we would let dv be what's left. So this would be our u here, and dv would equal f prime of x dx. Okay? This one we differentiate. So differentiate. And this one we integrate. So the derivative of u with respect to x equals 1. Well, we can solve for du. Du over dx is not fun. We really want to know du. So no fun, get back to 1. Do you see the big fat 1 in here? Dx over dx. And then times by dx on this side as well. If we're going to make this much bigger, then we need to make that side that much bigger. It's just 1 times du, which is just du. And this is just dx. 1 times dx is just dx. So du equals dx. And obviously u equals x. Over here, we're going to integrate dv. And so that equals the integral of f prime of x dx. Okay. This really, again, has a hidden 1 in here. We'll just do this. Keep this the same on this side because we haven't done anything yet to it. Okay. Well, if we take the integral of 1 dv, right, we're just looking for the antiderivative. So that's going to be v. And this is the derivative. The antiderivative of that is f of x, right? So v equals f of x. Well, f of x also equals y. So we can just put y there. Okay. So now what we're going to do is take all this information and rewrite this in terms of all this. So if we take the integral from 1 to 3 of x, f prime of x dx, then you can see that u equals x, so we can just make a u here. And f prime of x dx, so then we just put f prime of x dx is dv. Okay, so we are on the integral from 1 to 3 of u dv. And before, remember I told you that that's the same as, let me write this down here. That is the same as this. Okay, and so all we need to do now is just substitute things in here. So we know u is x, right? So what we're going to have is an x here. And dv is f prime of x dx. I get a little frustrated sometimes. I think everybody does when they do math. And so it's not math really, it's just a lack of space on my desk top and trying to make sure that it's clear that you can see it when I video it. My setup is not the best, but I try my best here. All right, so u is equal to x and v is equal to f of x, and so I'm going to substitute that in here, x, f of x, and then v is equal to f of x, and du is equal to dx, so I just put f of x here and dx here. Okay, So now if we look at our rectangle, we'll just leave this here. This is telling us to take the big rectangle and subtract the small rectangle from it. That's what this means. And then this says to subtract the area under this curve here, which we know what that is because they've given it to us right there. Okay, so let's just do this. This will be the big rectangle, which is 3 over and 6 up. 3 over and 6 up. Okay, subtract the small rectangle, which is 1 over and 2 up, right? And we're going to take all that and then subtract this, which is 8. And so 3 times 6 is 18. I don't know why I put minus there, that's times. And subtract 1 times 2, so 18 subtract 2 is 16. So that's just 16. And then subtract the 8. Well, 16 subtract the 8 is just 8. And so the area above the curve here is actually 8. So this answer here would be 8. Okay, but let's just look at things just a bit different here. Let's just look at this a little bit more. Okay, if we look at the integral of x dy versus the integral of y dx, this would be width, right? Because x is width, and y would be height, and then dy would be a little bit of y. It's a little bit of y going up like this. And so what we have, width times height and height times width, okay, because this is really a rectangle that goes like this, and this is a rectangle that goes like this. You have your height, your y, and then your little bit of x here, your width, and then here you've got your width, which is x, and then your height, which is a little bit of y. So these are horizontal rectangles, okay, which would go here, okay, and these are vertical rectangles, which would go here, okay. If we want to know what dy is here, right, obviously dy dx is the same as f prime of x. If we use no fun, get back to 1 times by dx here on this side times by dx on this side, dy is equal to f prime of x dx. Okay, which means that I can change this dy in here to f prime of x dx. Okay, well, if you look at that, those are those horizontal rectangles, and they have to go this way. There's x across and a little bit of y up. Okay, and that's what we're looking for here. Okay, and earlier we found out that dy equals dv, so this is the same as dv. Okay, and u, remember in this here we had uv, and we found out that u is actually equal to x, and v is actually equal to f of x. So really what you can change this to is this one here is, I'm just going to erase this here, erase these here, erase that there, is that this could really be the integral from u dv, which is just x by a little bit of y, right? Because this was the same as dv, right? And this you can change to v, because v was f of x, and you can see that in there, and du was equal to dx, so you can put du there, so you got v du, which is really interesting. Now this one here, this one here, if we use this, we can turn this sideways, okay, because u is across and dv is up, and so you could kind of look at it like this, from 2 to 6, that way. Okay, and this, we would do 3 and 2. Sorry, 3 and 1. That's if we're looking at it this way, from here. So it's interesting, you could turn it this way and look at it from 2 to 6, UDV, or go look at it this way. This would be the wall view from here, like from 2 to 6. This would be the floor view, this being the floor, and that being the wall. Okay, and we could also change this to this, because U is equal to X, and dV is equal to dy. We found that out earlier when we integrated. Okay, I'm trying to think what else I can show you on here, because I want to give you some little things here. This is the floor view, that's the wall view. Like this could be equal to U, this could be equal to V, okay? And so this is where you get all this UV, right? There's X, there's F of X, right? V, that's the same as F of X, right? And X is the same as U. And then of course we're going to do these on our bounds like this, right? So I'm just showing you how like this rectangle that I've built really kind of, all the parts match here, right? And so this area here is this area under the curve here. And then this area here is the area above the curve here. And then this UV on, sorry, this should say 1 to 3, is just the big rectangle. So 3 times 6, subtract the small rectangle, 1 times 2, which would be 18, subtract 2 gives you 16. Subtract the area under the curve, which is 8, and it will leave you with this area here, which is also in this case 8. And that's just because for whatever reason, this has split this into 2 equal areas. And so this part here is just UV, the UV equals 2 part, and then this bigger part is the UV on the 3, right, the 18. I hope I'm not losing you guys on this. It's very interesting. I don't know if I have a lot more to say here. Basically, there's a whole lot of moving parts here, but really it's just same as. So for Mortensen math, same as, right? This is same as that, right? This is same as this. It doesn't look same, but it is same. All of this is just referring to this. And then all of this here, y dx, right? And b, this is just, and we should put this on here. This should be 1 and 3, and this is just y, which is f of x, right? And dx equals du, right? So I can just put that there, right? That's this here, right here, right? All these things are just different ways of saying the same thing. So same as, you know, it doesn't look same, but it is same. Part of our Mortensen math thing, you know, math is just the study of numbers. What do you do with numbers? Well, we just count them. We build rectangles to facilitate counting. Well, that's what I'm doing here, just using rectangles to facilitate counting. This really isn't a hard problem. It looks hard when you look at all of the different symbols and things like that, but once you understand all the moving parts, it's actually really simple. I'm hoping I haven't confused anybody today. What I did want to tell you guys, though, is if you look at this here as well, you can see that this line has a slope of 2, because you go 2 up and 1 over, right? 2 up and 1 over. So this really is just a line. And I'm just going to erase this here. If we actually look at what f of x is, f of x is a line with a slope of 2 over 1, right? Remember y equals mx plus b? Okay. Well, our intercept, if we carried that line down, would be 0, right? Because 2 up, 1 over, or 2 down, 1 to the left. I should really say 2 up, 1 to the right, 2 up, 1 to the right. In this case, I can do the opposite, 2 down and 1 to the left. And you'll see that the intercept is 0, so this would be plus 0. Well, really, f of x is just equal to 2x plus 0, so I'm not going to write that. Well, if I take f prime of x is just 2, right? And really, f prime of x is just the slope. Well, you can see that that's 2, right? If I were to do the integral of from 1 to 3 of f of x dx, right? And if that f of x is 2x dx on 1 to 3, right? Well, the integral for that, remember, this is the derivative. We want to go backwards. We want the antiderivative of this. So we would go 2x, and then there's a 1 on there, so 1 plus 1 is 2, and then over on the bottom 2. I'm not telling you all the rules with this. I'm assuming that if you're watching this, you somewhat know these rules, but maybe you don't, and maybe that's some things I'll have to go through. That just ends up being x squared. Well, if you look at x squared on 3 and 1, you end up with 3 squared minus 1 squared, which is just equal to 8, which is what we have here. Okay, so, I mean, we can logically work this through just by looking at the slope of that. What I wanted to do was show you guys that really all of this hard stuff is really just, it's not that difficult. Anyways, if I was to label this, this would be 3 and 6, which would be u and v, or x and y, right? And this would be 1 and 2. Again, u and v, x and y. This would be 0 and 0, right? That's your origin, 0 and 0. This would be the integral of u dv. And so I'm going to actually erase this. This in here is the integral of u dv. And that is going to be equal to u times v from the 3 here, right? This 3 to the 1, right? Which is the big box, subtract the small box, or the big rectangle, subtract the small rectangle, and then subtract the integral of v du. Okay, again, all of these should be 3 and 1, 3 and 1. Okay, well, we already know 18 minus 2 is 16. Subtract the 8 which we're given, right? So the integral of 1, 3 u dv is going to be equal to 8, and that's this up here, okay? And again, the u is x, and the dv we found out earlier is dy, right? And what am I thinking here? Yes, so x dy, and we went through this already. You know, if you solve for dy over dx equals f prime of x, well, dy equals f prime of x dx, right? When you use no fun, get back to 1. So it's like this big loop. It's really quite fun. Just think of this as your floor, and this is your wall. And this is your big rectangle, that's your small rectangle. Take your big rectangle, subtract your small rectangle, subtract the area under the curve, which generally in the AP questions are given. We did an AP question in the other video, but I didn't really show you that the small rectangle was just basically non-existent. There was no rectangle, so you're subtracting 0 from, so the big rectangle subtract no rectangle is just the big rectangle. And then subtract the area under the curve gives you the area above the curve. So that was my other video. I'm trying to show you all, it says integration by parts. There's so many moving parts here, so I wanted to show you all of these things. And also one other thing here is what happens with this, which I think is kind of fun, is that the integral of 1 to 3 of x, f prime of x, dx is equal to the integral of 1 to 3 of f of x dx, which is equal to the integral that because we did that line from 1 to 3 of 2x dx, and all of this is just equal to 8, right? This is 8, that's 8, that's 8, right? The whole, so 8, 8, 16, and 2, 18. I don't think there's much else to go over here. I'm sorry if I went too quick. If you have questions, just ask. If you don't understand integration by parts, that's maybe something that we should go over a bit more. But basically, integration by parts is you let u equal something, you differentiate it, you let what's left under the integral to be dv, and then you integrate that. You integrate both sides of that, and again, with differentiation, you would differentiate both sides, and you end up with a u and a du and a dv and a dy and an x and a u and a v, and that you just substitute all those things in, right? Just things that are same. You can just, if they're same, you can substitute them in. You can like use one for the other, and then you just use the integration by parts formula, or you can just use common sense here and just kind of work it out, right? It's a big rectangle, subtract a small rectangle, subtract the area under the curve, leaves you the area above the curve. And that is what the integration by parts is. That's this formula here. U dv, the integral from a to b of u dv equals the two rectangles, the big one subtract the small one on that same thing, and you and subtract the area under the curve of the function. And that's what this is. Okay, that's this part here is equal to the big rectangle, subtract the small rectangle, subtract the area under the curve of the function, and you're left with this, right? And again, we did that. 18 subtract 2 minus 8. That one's given to us, right? Well, that's 16 minus 8 is 8, right? So 8 equals 8, right? Anyways, I think I'll stop there. I really hope this video is helpful. If it's not, I apologize. This is my first attempt at really trying to use base 10 blocks to show some of the higher level calculus concepts. In this case, integration by parts. So that's what this is called. Let's just do this. This is called integration by parts. Okay, this is the lower bound, that's the upper bound. This is the area above the curve. This is the two rectangles, the big one subtract the small one, so big one subtract the small one, and this is the area under the curve, and it's integration by parts because there's just a lot of parts, right? You see how there's one big part, one small part, area up there, another part, it's just parts, right? That's all it is. Yeah, I can't really think of much else other than that. I feel like maybe I've thrown a lot at you, but really, it does get easier the more you do it. So look at integration by parts, see if you can, if you have blocks, see if you can do them. If not, just draw a little diagram, right? Just draw a little diagram like this. Right? This is the integral of u dv. This is the integral of v du. And this is the big thing minus this, right? That's this here, right? The big rectangle, subtract the small rectangle in there. You could look at this as your floor. You could look at that as your wall. Then if you turn it sideways, your bounds can change. And if you are in... if you are doing UDV sideways from the wall view, it looks a little different than the floor view. I think that's about it. I'm going to stop there because I don't really know what else to add to this. I think that is about it. yeah, hit me up if you have questions. Feedback, if anybody has feedback, if there's something I'm saying that's incorrect, or could be tweaked, just let me know. I am really, really stoked about trying to show you how you can use base 10 blocks to explain different concepts, big concepts like this, just with base 10 blocks, right? And I mean, look, it's 3 6s and a couple of felt markers, right? That's what we're using to show this, right? All right, that's it. Have a good day. We'll talk to you later. I guess one other thing is, if you want to see different videos on different calculus things, let me know, because I'm quite open to making them. I really want to I love Mortensen math and how simple it is for the arithmetic, the algebra, and things like that. But I do think we need to take it to another level and show just how we can use Mortensen math blocks to show higher, like, calculus concepts like this. Okay. All right. That's it. Bye.